Hey everyone, this is FM Mathematics. I'm going to present cosine identities where you can take the power of any cosine and then equate it to any sum of cosines that are all going to be to a single power. So the identities we're going to need are the first is Euler's identity, where we have e to the theta I equals cosine plus I sine theta. Then you're also going to need to know how to change cosine to a function of thetas using Euler's identity. And we are going to use the binomial expansion where it's going to be 1 plus x, not the generic one where it's y plus x. So, moving on, we start with our binomial expansion. We substitute e to the 2 theta I. So e to theta I in the substitution, of course, you see it's pretty plain and simple. Now, why we're using 2 theta I, you'll see as we come down through the steps of the equation. So the next step is going to be where we actually pull out e to the n theta I from that from the power. So you can kind of see what we're doing here. We're kind of forming it up. We've already set ourselves up to where we know what cosine is supposed to look like when you have e to the theta I. So we're just forming it. And the next step, we show that we need that 2 in the denominator. So we pull out a 2n to get that 2 in the denominator. Now, for our next step, what we're going to do is take the 2 to the n, and we're going to put it on the other side by dividing by 2 to the n. And for the next step, we're going to take the e to the n theta I, and we're going to put that one on the other side of the equation. So in this case, you're going to have e to the negative n theta, and e to the 2 minus n theta I, and so on and so on. So on the left side now, we have just the expression for cosine to the n power, as we see here. So technically, we've really just accomplished the mission where we finally have an identity for cosine to the n power generalized, but it's a little bit ugly. It's a lot bit ugly. We have it all in terms of the exponential, which we don't want that, right? We want it into cosine terms or sine terms. So we will take Euler's identity, and we're going to kind of fix it up a little bit where we have k to the minus n theta I. So what that k to the minus n theta I is going to do for us is, once you see how we follow in the steps, it's going to allow us to take the terms that we had on the right side, where they were in form of 2 minus n and 6 minus n and 4 minus n, and now we can split our equation to its own cosine and sine terms because we know what all of those e's are. So if you see on the top, we have e's in all the terms, and you see on the bottom, now we have a sum of cosines and I times a sum of sines. So keep in mind though that the left side is a real number, assuming you have a real number for n. So if it's a real number and we're equating it to a complex function, then the imaginary side of that complex function must be 0. There's no other way. So we simply just discard the imaginary side. Now, if you want to use it as an exercise for yourself to see that the sine part of that function is in fact 0, be my guest to try to throw any number you can in there that's gonna converge. It will always converge to 0. So now we have our formula, our general formula for cosine to an n power, and equating it to the cosine of single powers all summed together. And please recall that if we have k greater than n and n choose k integers, I should have put on there that they have to be integers, it's going to be 0. Now what that means is, in my cosine to the n power identity, once once k is greater than n, all those terms zero out. Again, assuming that you have an integer power. So we can split this even better. And so we can split it and improve it to where we have an even formula and an odd formula. And this makes things a whole lot more simple and makes things make a lot more sense. Because if we have it to our even power, you'll see that it ends in a constant. If you have it in the odd power, it does not end in a constant. You also see if we have it in an even power, it's going to have an even coefficient next to the theta. If we have it in an odd power, it's going to have an odd coefficient into the theta. Not only that, it's going to start with whatever the power was and then move down. So this is a really, really easy way to remember that these formulas, to where you don't have to do a reduction formula. You don't have to try to break it down. You don't even have to really look into a book to see what these identities are, because there's an infinite amount of these identities depending on what power of cosine you're using. So this eliminates a whole lot of steps. And we're going to show that by showing some examples. So the first example is the one that we all know and love, right? We have n to the second power. And so n to the second power, we're going to need to use our even formula. In our even formula, we make k 1. So I have reiterated my even formula to show what the form actually is. Then I've substituted my k equals 1. So I have cosine squared equals the 2 choose 0 cosine 2 theta plus 2 choose 1 divided by 2, all divided by 2. And so for choose 2 0, it's 1. For 2 choose 1, it's 2. And then we have our identity that we all know of cosine squared equals cosine 2 theta plus 1 divided by 2. Now, something a bit more exotic than that one that we don't use a whole lot, but we might run into in calculus, is if we have n to the fourth power. So, or if we have cosine to the fourth power, rather, we're using n equals 4. So this is, again, we're using our even formula, and our even formula, we're going to have k equal 2. So when k equals 2, we are starting again where we have cosine 4 theta, and it's going to be multiplied by 4 choose 0, which, you know, is always going to be 1. So just for the order of things, I keep it in its form where you have n choose 0. But yes, we have 4 choose 0. We have 4 choose 1 cosine 2 theta. And then that's going to be added by a constant, just like it was for the squared version, because it's an even power. So when you break all that down, you get cosine to the fourth power equals cosine 4 theta plus 4 cosine 2 theta plus 3, all divided by 8. Now, we're going to go even more exotic to something that would be a real pain in the butt if you had to use any other method other than this. So we're going to have n equals 7. It's an odd formula, and in our odd formula, we're going to go ahead and make k equal 4. So with k equal 4, we throw everything in, we do our substitution, we have cosine to the 7th power equals 7 choose 0, 7 choose 1, 7 choose 2, 7 choose 3. So if you notice, normally in a binomial expansion, 7 has 8 terms. To the power of 7 will have 8 terms. And here we have 4 terms. And it's the same for the evens, except evens you're going to have an odd number of terms. So your odd number of terms, you minus 1 and divide by 2, and you get how many terms are not constants in your even terms. You don't really need to know that, because you can kind of see how everything forms up, and it's already in the definition of where to stop when you're doing the summation. But I figured I would point that out, that that's something easy to remember, that when you're doing the odd powers, it's half the amount of terms that would have been in the binomial expansion. So, yes, we have 7 choose 0, 7 choose 1, 7 choose 2, 7 choose 3. All simple, pretty easy. You're starting with, again, the power, so cosine 7 theta, because 7 was our power. You're subtracting 2 to make a 5, to make a 3, to make a 1. And every single time these forms are going to happen. So, and then you're going to be dividing by 2 to the 6th power. So 2 to a power that is less than the cosine's power. And that's always going to be what's in your denominator. For odds, that will always be the one that's in the denominator. For evens, the problem is that your constant is also divided by 2. So your constant is not going to be divided by what 1 minus the power, but every other term is going to be. So that makes things pretty easy, I think. If you know the binomial expansion, you know all your identities for cosine when it comes to integer powers. Now, throwing a monkey wrench in this, and this is something that a lot of mathematicians like to do anyway, is they want to throw a number in there that doesn't particularly make sense. So I'm going to go ahead and throw n equals -1. Now, throwing n equals -1, I can't use my even powers and my odd powers. Why can I not do that? Because my even powers and odd powers formula terminated. They terminated because when k is greater than n, and they're positive integers. I should have said that. They're positive integers. It terminates and it ends. It becomes a finite sum. If it's not, it's not a finite sum anymore. And in this case, what we have is cosine to the -1 power, which cosine to the -1 power is secant. So it's kind of silly, right, that we're coming up with an identity for secant, even though we know secant is just 1 over cosine. But it's interesting to see what you get as a result, because what you get is that secant can or may equal 2 times cosine plus cosine 3 theta plus cosine 5 theta plus cosine 7 theta. Basically what it equals is all the cosines where there's an odd coefficient in front of the theta. Now, if you were to test this by putting values in, you're going to get one of two things. You're either going to get something that just oscillates for infinity, or you're going to get something that ends up becoming infinity. So if you, for example, put a 0, you're going to have that 1 equals 2 times 1 repeating. Now, what is interesting about this is kind of related to, if you've ever heard of the zeta function. So formally, 1 plus 1 plus 1 plus 1 repeating forever actually equals 1/2 formally. So this is kind of the same thing, where although I don't really have a value that's going to converge, I can have a formal definition of a value that diverges to where it actually equals a constant value. Now, the interesting thing would be to integrate this. So I actually leave that up to whoever's watching and wants to have a little bit of integration practice, is to go ahead and integrate this between 0 and 2 pi and see what you get as a value, and test that value to see if the integration was correct. So that's my presentation. I hope that it was informative. I hope that you can use this in calculus, and I hope it all makes sense.